Without not much preparation, and since Owen is introducing somebody else in another room, let me introduce the famous Michael Feather.
Thank you. I'm spending an awful lot of time thinking about this over the years because I see so many bad examples of it. And it's kind of striking to me in the sense that when we kind of look at a lot of the design literature that we have in the industry, I mean, we've had design patterns for ages. We've got various different books about how to approach object-oriented design, systems design, things along these lines. It seems like nobody ever really goes and talks about this one, I've looked around a bit, and I just don't see all that much. And it's really kind of funky, and it's really kind of weird, because it is something we can kind of botch up pretty easily, right? Or it's something we can kind of trivialize in a way. Sometimes I'll talk to people about, handling errors, and they say, oh, exceptions. We've got exceptions. So if we have exceptions, we've got an error handling policy. Yay, Is that true?
No.
Yeah, no, it's kind of weird. I mean, it's funny that exceptions are almost like the be-all, end-all, catch-all, well, no pun intended, way of going and dealing with errors, right? And the theory really is that, something bad happens, and then what happens? Flies up the call stack, and then you catch it someplace. And then there's always that question, what do you do, right? And quite often people don't think about that question when they are designing a system. They just think later, it's like, well, bad things are going to happen. I'll be able to catch it someplace and do something. Shoot, what should I do, right? So I think that we really suffer from the fact that we don't really go ahead and consider error handling itself as a first-class consideration in design. And I hope that we can kind of move forward to go and sort of arrive at better ways of understanding this. And I've got a couple of different ideas about this. So this talk in particular is going to have a lot of stuff in different areas. It's going to go and relate some things I've kind of learned. And I think towards the end it's going to kind of devolve into a bit of a conversation in a sense, because I want to get your guys' feedback about some of these things also. Doubtless there are things that I haven't thought of that you guys have thought of that would be a very useful adjunct to this sort of thing. So the thing I want to go and confront first is this. I remember seeing a paper a long time ago where they said there's one way to go and handle errors that is just better than all other ways of handling errors. And that way of handling errors is to fail fast. Does everybody know what fail fast means? Okay, it's kind of like as soon as you encounter some kind of a problem, what you do is just sort of throw an exception or something and just get out. And once you get out, it's like somebody can look at the logs or whatever and figure out what to do. Sounds like a good idea, right? The thing is, it kind of threw me when I first saw this paper that was describing this, because I'd worked in an embedded environment for years, where essentially you were making systems that had to run. They just had to continue to run forever. Okay, you just really didn't have the option of going and saying, hey, I want to go ahead and just get out of this, and then let everybody go and sort of deal with the errors as they occur. And this really kind of struck me rather tightly, is that essentially there is this thing that really, error handling policy is not something we can kind of look at as being something like a one-size-fits-all solution. There's no universal best way to go and handle errors. And because of that, it really has to be a matter of design. We have to design our error handling policies, and we have to make sure that they really work in the context of the code that we are developing. So I kind of classify these things into two different areas. I think that in general, what I've seen in the industry is that you have two different kinds of systems. You have attended systems and unattended systems, right? And I think when we're living in the web world as we are today, quite often we are in this attended world, which is nice. Okay, we're able to go and say, look, we're doing various different things, and something bad can happen. But guess what? We've got production support right there, and they have their beepers, right? They have their cell phones. We call them for 3 a.m. and they just sort of fix the problem, right? And in fact, I think this is one of the things which actually goes and makes the use of dynamic programming languages that we use, today in a lot of web development much more easy to tolerate and thrive with. Actually, is the fact that if something goes wrong, there's somebody there you can take care of it, because guess what? You're running on your own servers. You can kind of move on and do some good things based upon it. But there is, as I mentioned earlier, there's this whole other class of systems which just have to continue running no matter what. And when I was working in this embedded area, it was really amazing to start to think about how to make that happen, right? Because you're thinking, well, maybe I've got a programming error in there. Or you're thinking, well, maybe I'm getting invalid input. And it's like you're even down to the point sometimes of going and saying, look, I'm going to actually produce incorrect results. But as long as my system can continue to keep running, that's fine. And that's actually something which is really a valid choice in many different systems. So This is something which was really impressed upon me in this work that I was doing. I worked in embedded for a while, but I also worked with a bunch of scientists who were developing instrumentation. And they were developing instrumentation for experimentation to make other instrumentation, okay, which sounds like a kind of meta thing. But the cool thing is I was the programmer on this project, and we had to go basically do all this kind of machine control stuff. And I just noticed that it was really kind of striking to me that actually they could tolerate, back in the old days, Windows NT, they could tolerate a blue screen. The scientists didn't mind a blue screen where basically everything had crashed in the entire system, as long as they never got bad results. Okay, they were actually happy with that. They said, just never, ever, ever produce bad results. And that's just the way things are for us. But within the same company, we ran into the other issue, which is kind of like, okay, we got this thing which is going to kind of run forever. And it's like the time it would take to kind of reboot the machine and do all this stuff to keep moving on with things was so large that we're just better off saying, look, for some of these things we have to go and actually just keep on marching through, no matter what. We have to go and figure out how to go and march through with these things. So those are rather key different domains. And it's kind of funny because I think, unless you've worked in those two domains, you probably live in one world or the other. And you look at it and you say, okay, well, it's like this is the way errors should be handled. But I think it's time to go and really talk about the fact that really there are different policies of handling errors. And this really should affect deeply how you design your code. So the types of errors I'm going to talk about here, just to provide a little bit of context, because error is such a very large, it's a term which means so many different things. I'm going to talk essentially about the kinds of things that we induce ourselves as programmers, right? Things that we do accidentally in our code which end up producing bad results. Or abortion, basically aborts the process or something along those lines. The other types of errors I'm going to talk about are things like device failure. Okay, so I am, if you're looking like in the embedded domain, it's like I'm doing something which is going to go and tell a solenoid to go and do something along those lines. Or you can just say, even in the non-embedded domain, it's like I'm working against a hard disk, and hard disk could crash, right? I'm talking to the network, and basically something could go down with the network. So that's another type of error that we're going to talk about as well. The other type of error we're going to talk about is invalid input. Okay, the notion that sometimes you're working in a system where you're getting inputs from other systems, and some of the inputs you're getting are from other people, people who are manually operating a system, and they can give you the wrong stuff. All right, so you have to kind of figure out how to go and deal with these three things. So the philosophy I've kind of arrived at with this, after seeing a lot of systems and stuff and talking to many people, is that it's really great in an application to go and try to organize things so you have a safe zone. Okay? What I mean by this is that you're really better off, whenever possible, going and pushing detection and recovery of errors to the edges of the system. Okay? And it's a funny thing about this, because if people don't really think about this, they end up with all sorts of crazy things. In particular, where you have things like, okay, I got a big old cache handler over here, and I go way down and call stack, and then I throw, and I'm right back up here again. And it's like, okay, what do I do when I'm back up here? This kind of thing. It's nice to actually deal with things at the edges, so you can say things like, okay, well, look, I'm receiving input from a user, and I should be able to tell them pretty quickly whether that input is good or bad, right? I should be able to validate it. But from that point on within the system, I don't have to worry about invalid input anymore. Right? If I'm inside the system now, I know that what I've got is valid, right? I should be finding that out halfway through a computation. Okay? Now, the thing about this is kind of funny is that sometimes that's practicable and sometimes it isn't. Okay? For the most part, though, it is generally practicable. There are very few things that you do that you can't sort of know ahead of time whether you're actually going to be able to do them or not. Okay? And if there are, you can kind of handle that sort of thing. But that class of things is really the class of things which was really defined first by Bertrand Meyer as the class of things that exceptions are good for. One of the things he said, and I don't have an exact quote of this, is that use exceptions when you can't tell ahead of time in a computation that it will produce the results that you want to. Okay? And when you think about where that sort of thing typically happens in systems, quite often it's I/O. Right? It's kind of like my I/O system could fail. I'm going and grabbing input from someplace else, and wow, this socket could just sort of fail, and I'm going to get nothing. So you typically see this in many systems. You have exception handling around the edges of the system. But sometimes what people will go and sort of put the upper level handler, which is way up high above all the other work that needs to go and happen. And there can be some awkwardness about this. So when you start thinking about things which can happen inside this safe center in an application or process, these are the kinds of things which can happen. And there are many others, but just a partial list. Things like numeric overflow, null dereferences, things along those lines. And general programming errors, right? Things that we do which end up going and producing bad results. Okay? So what do we do about these things? How many people ever deal with null pointer dereferences as a problem? I mean, oh really? Oh wow. I mean, we're all Agile here. We should get past this, right? That's one thing I hate with a passion, though, is null programming languages. And it's kind of neat to go and see people talk about this a bit more, but I can't tell you the number of places I've visited where essentially people have null checks all over the place in their code, right? And you look at that and you say, okay, well, you know, that's fine and everything, but it really obscures all the logic and all the computation and all this other stuff. And you think about, well, what would it take to not have all these null checks in the code? What does it take? Sorry?
Null objects.
Null objects? I mean, yeah, that's a particular solution, but the key thing is really avoiding passing null, right? And whenever you have a computation which produces null, try to convert it to something else so the rest of the program doesn't have to care about it, okay? Because null itself is something which is just like a little bit of a time bomb. You have to check for that time bomb over and over again in your system. And when you don't know how far that time bomb can go in your system, you're checking every place, and you obscure all the logic, and things get kind of crazy, okay? So, I mean, there's things like this that people really ought to know when they're designing systems. The thing which is terrible about this null, dereference problem is it's just so damn pervasive, all across the industry. And it's like it's really, really hard once it's pervasive in a code base to go and actually do something about it. Because you're sitting there saying, okay, well, I think I can go and, I think I can set things up in such a way here where I don't have to go and check for null. But you're surrounded by all this other code that checks for null, and you start to feel really paranoid. You're kind of like, it's like, I'm not checking for null here, and everybody comes after me is going to think I'm a real jerk because I'm not checking for null, but I kind of know it's not going to happen, and it has to be an understanding that you have that you can move forward and do this sort of thing. And it's tough in the context of a large existing code base. For newer code bases, just having that rule. We never pass null. When we get null from an API, we convert it. Having that kind of thing makes your coding much, much saner. Okay? To give you another example, which I think is kind of funny about this, there was a company that made a tool a long time ago to go and develop automated tests for existing code bases. And it's like, isn't that pretty cool? I mean, we wouldn't have to do TDD at all, would we, right? We could generate tests all the time. No, so that's like that pipe dream, right? But people keep trying. They keep trying over and over again to do automatic test generation. And it's like, there are some forms of it which actually can be rather useful in that sort of thing. But a guy was demoing the tool to me, and he was basically showing me various things. And we ran it against some of my code, and one of the things it came back with was, oh, wow, in this particular area, you're not checking for null, right? Because we passed null and we saw that it failed. And it's like, this is all inside of a library that I've written. And I said, well, that doesn't do me any good. And he's like, well, what do you mean? And he says that those are errors, right? I mean, it's like, if somebody passes null, your program's going to blow up. And it's like I'm saying, no, people shouldn't pass null at all, right? And it kind of got me back to this metaphor in a sense that what that tool was kind of like arriving at was something like, imagine in your house where every single hallway and room has a lock on it. So to walk from the living room to the kitchen, you have to go open 3 doors with separate keys or you're going to get to the place you need to go. So it's like, in a house like that, it's really a pain to move from place to place. It's really a pain to go and do anything in a house like that. What we end up having in homes, generally, are areas of trust. Where basically you can keep an open door because guess what? You know that the only people that are in your house are the people who should be able to go back and forth between these 2 rooms. And in much the same way, I feel that with error handling and things along those lines, particularly input validation and stuff along those lines, those things need to be at the edges of the system where you can say, look, once we have gone and produced, once we've actually gone and sort of said to ourselves, we've gotten sane, then everything else is left upon us and we can basically say, look, there's not much we have to check for because we know what our entry points are. We know what our entry points are, and once we know what our entry points are, we know what is sane in this context within our code. And so I think it's a very valuable thing to kind of strive for in a code base. Does anybody work in a code base where you don't have null checks all over the place? Yeah, that's pretty cool. So how'd you do it?
Perl.
Perl? So maybe somebody say Haskell or something like that. Yeah, I guess whatever works, right? Yeah. So I'm going to go and sort of lead into some other stuff now, and I have to go and sort of define the term. This is what I'm sure many of you have encountered. Anybody with like a mathematics background has run into this concept. The notion of a total function and the notion of a partial function. Okay? And this is just really something which is really just general in mathematics. The notion is that essentially if you have some function on inputs, there are some functions which are organized in such a way that they will always give you a result for any input that you supply. They'll always give you a valid result. There are other functions as well which basically have certain constraints. It's like if you pass some value into it, it's just not guaranteed to go and give you any valid output. And if you're familiar at all with like the notion of design by contract, I mean, yeah, design by contract? Yeah, okay. Old notion, again, from Bertrand Meyer. He kind of discovered a lot of things very, very early in object orientation. But his notion was that for methods, what you could do is you could say, look, I'm going to go and list out what the preconditions are. And if we pass values in, you should look at the preconditions first, because that will tell you what is acceptable input for this function. And once you've given it acceptable input, then you're guaranteed to go and have a valid output. And just that understanding of how things work in a system is a very valid thing to go and have. Now, the thing that's kind of funny about this, though, is that people don't generally do design by contract all that much in the industry. They don't sort of sit down and list out exactly which inputs specifically are valid for particular functions. And so a lot of this stuff is really stuff which is kind of communicated informally to us across, across the code base. People looking at the code and trying to get a sense of like, okay, well, it's like I can see where passing this isn't going to work, so I can kind of move on and pass something which is a little more valid than that. A great example of this is one that we're all kind of familiar with, knowing math. What does that produce? Excuse me? Is there an I in Java, though? And that's the funny thing about it, too, right? I mean, essentially, when you look at it, by the spec, okay, yield's not a number. Okay, so what is not a number? You could argue it's a number, but it's one of the strangest numbers you'd ever encounter, right? Okay? I mean, it's really this value which represents the absence of a valid result. And what is not a number added to not a number? Not a number. What is not a number times not a number? It's not a number, right? It's like this black hole of value, in a sense, right? But it's an interesting thing about this, though, because this pattern that basically people stumbled upon very early was this notion that, wow, what we can do is we can use a special value to represent this sort of thing. As long as we basically make sure that it plays well with other things, we can sort of kind of just proceed in a decent way. So you can have a whole bunch of chain computations, and lots of additions and subtractions and multiplications and divisions and matrix arithmetic and all this other stuff, and it will all run to completion, but you just may get not a number at the end of it, right? And then, of course, you've got that issue of like, damn it, how'd that happen, right? And when you're dealing with that sort of thing, but the thing is at least you aren't getting an exception when you're dealing with that sort of thing. And it's a choice that people are making, because in some cases you really do think an exception is actually a very decent thing to do. Quite often divide by zero. Someone's just going to throw an exception, because it's just really so serious, that people just consider that that's something we have to avoid and get out of. But those decisions were made kind of early on when people were establishing floating point arithmetic libraries and things along these lines. The thing that's cool about not a numbers, it's kind of, I'm calling this an in-band calculation board. For lack of having any other terminology. Maybe this might be a little better name than this. But there are other things that are like this in programming. I don't know if anybody here is familiar with Haskell at all. Haskell programming language? A little bit? Yeah, okay. Safety is paramount in Haskell. It's a functional programming language. It's statically typed, and it goes and allows you to create some very, very safe code at the expense of thinking like a Martian. Okay? But the thing is, once you get into it, it's kind of like thinking like a Martian is pretty damn cool, right? It's neat. They have something like this. They have something called the maybe monad, and it's kind of like a maybe. It's kind of like a data type where basically it represents the end result of a computation or something called nothing, right? And the cool thing about maybe is that it's kind of like, well, when something produces maybe, you can't sort of dereference it and say, oh, give me the result, and not check it, because it uses pattern matching on this in order to go and actually allow you to do something. You have to have like this, almost like a switch case thing, where you say, okay, I've got this maybe result. In the case of nothing, I do this. In the case I've got something, I do this. And it's kind of funny when you think about that. That's kind of like a way out of the null problem in a way, isn't it? It's like there's no way to dereference null, because you're matching against null, or matching against the fact that you don't have null. And it's like you must deal with the error at that point. You must deal with a particular thing. The other thing, though, as well, is that in Haskell, when you have maybes, you can have computations which produce maybes and accept maybes also. So you can start doing this chaining thing, just like you would do with not a number. It's rather convenient. The thing I want to talk about more about this, though, is really that there's another way of going and solving this. And it came back to whoever it was that's jumped up and said, pi, right? Imaginary numbers. What you can do is you can use domain extension and range extension to go and basically get past error conditions, or get past things that are possible error conditions in your code. This is another way of approaching things, handler objects. This is really a very old pattern. I was talking to Martin Fowler the other day over lunch and talking to him about some of these things, and he mentioned this pattern. He didn't have a name for it, but I used this on a system, embedded system a long time ago, where we simply didn't want to use exceptions at all. And the idea was, what we did is we basically took this object, we kind of passed it around through the system. Every time it got passed from one place to another, if there were errors, the errors themselves were kind of sent to the handler object. And then the assumption was that the code could continue at that point. Okay, so you're reporting an error, you're not really choosing to abort, but the thing that's kind of cool about them is that you can. You could actually, if you wanted to, throw an exception within a handler object. Say, look, whenever something goes and happens, I just want to go ahead and say, look, I'm wanting to call a stack, I just want to go and get out of here. Or you can say, look, all this stuff that we're doing, it's like we're just going to go and log it. We're going to log it, log it, log it, log it. And after the computation is all the way done, we can look at that log and find out all the bad things that happen inside the context of our code. This is another way of going and dealing with errors in the system. So another decent mechanism. So we talked about error-related patterns and practices. I was trying to find a good name for this one. It's a funky one because it can be really kind of deceptive, but it can also be very useful sometimes. Error feint. Okay. Avoid an error check by making incorrect use innocuous. Okay, I'm sure all of you have done this at some point in time. We have a little class here called formatter, and what it does is it allows you to basically add on new text and new lines and stuff like that into the formatter. And you're able to do this thing here. You're able to go and indent, and you're able to outdent. Okay? So you can say, look, I'm adding text, I'm adding text, I'm adding text, I want to indent. And what it does is basically it sets the indentation level so that all subsequent lines will have the indentation added to them whenever you add a new line. Okay? And it seems like a decent protocol for doing this sort of thing. But then you got the problem, which is just kind of like operating with a stack, right? It's like, what happens if outdent is called too many times, right? It's just like with a stack. How many, it's like you call push 3 times. If you end up going and calling pop 4 times, you're really in trouble, right? So you have to go and deal with this constraint in any code that you have which goes and uses this particular thing. So, some people might look at this and say, okay, well, this is what assertions are for. We can have an assert statement that goes and says, look, if our indentation length is greater than 0, then we can go and outdent. If we can't, it's a problem. And if it's a problem, okay, assertion. What do? We can kind of blow up with the assertion, or depending upon how assertions are configured in this system, and we're either going to find out about it now or log it and hold on to it and find out about it later. But there's an alternative to this. The alternative is to go and do something like this. Say, look, we're just going to go ahead and check here and say, look, if indentation length is greater than 0, okay, we're just going to go ahead and basically truncate our indentation, okay, have a smaller indentation string. If it's not, we're just going to ignore it, okay? People can call outdent too many times. And that is really a programming error, okay? But the thing is, we know that we can kind of we can basically go ahead and recover gracefully from that. And even if that coding error remains in the code base for a period of time, it's actually okay for us to just sort of say, look, we're just going to go ahead and give this a pass. It's like, if somebody goes and calls outdent too many times, no big deal. What we could do is we could log it, make sure that somebody goes back and fixes the bug. But at the very least, we just know that this is something we can kind of go and deal with. Okay? So an error feint is kind of like this. It's essentially this way of going and saying, look, I'm going to go ahead and sort of normalize the computation in a way which is going to possibly produce incorrect results, or maybe not, just be more liberal in the way that it accepts input, but still not allow us to, not force us to win a board in our system. Another thing to talk about too is this practice, I think, is kind of cool, designing away preconditions. I mentioned design by contract a bit earlier as a very powerful thing for us to do when we're developing software. But the thing that I think is really kind of funny is that people quite often, when they hear about design by contract, they miss one thing which I think is very, very important. And that's that if you have too many preconditions for some piece of code, it means there's probably some kind of a problem. Okay? If you have this particular method that you want to call, and you've got like 5 clauses of constraints on the arguments, constraints which basically tell you, well, you can't really pass that in with this thing, and you can't pass that in with this thing, and that thing with this thing. There's probably some way you can organize your code to make things better. And it's going to make things less error prone, and then you're going to be much better off in the end of it. But the fact of the matter is that preconditions are really, they exist. It's kind of like there are certain things like passing a negative number to the square root function, where you're going to say, look, I could extend that out into the range of complex numbers, but I don't really want to. So having a precondition saying everything has to be non-negative is great. But the thing I think is important for people to realize is that these things really aren't choices. You often do have other ways of organizing things. So you can basically look at those things. And as you try to reduce preconditions, you can make some things a little bit clearer. So take a look at this example here, okay? A typical thing in many applications is a thing like a date range, for instance, where you go and pass in like a starting date and an ending date. And there's all sorts of questions about this. It's like, okay, is the end inclusive or exclusive? What if the end is less than the start? And that's a classic thing. It's like if you do that, you really want your program to blow up, and somebody goes and gives you, the end prior to the start. Or you can go and choose to go and basically define that and say, look, if the end is prior to the start, then it's just really an empty date range. And everybody just has to kind of understand that that's a possibility. Okay? But still, you end up with this thing where basically the intention of the programmer doesn't really match what these results happen to be, and it's kind of awkward. So an alternative with this, and I'm not arguing this is a great way to do this, but just going to demonstrate this concept, is you're going to say, look, we create date ranges based upon a start, but then we basically have an added a set of calls we can use to essentially inflate the range. Okay, we can say, look, we created the range just on start point, and then now what we can do is we sort of inflate it with a couple of different calls. We can add weeks to it, we can add days, we can add hours, we can add seconds, things along those lines. But the thing is, we're knowing that we will always have a valid range when we do this. Okay? The mistake would be if somebody chose not to inflate it, or they chose to inflate it wrong. But the thing is, it's all explicit that you have to put down there. It wouldn't be a hidden error like this, where basically your end's prior to your start by looking at the code. Okay? So these are things that you can do, and I think this is an important thing for us to think about, that you can design away preconditions, and having too many preconditions is really an awkward thing. Okay, special case object. There's another thing we can do. I'm not going to go and talk much more about this because we did talk about it a little bit earlier. This is kind of like that null class thing I was talking about in Ruby. Your methods goes and returns just an empty list when things are when we don't have anything. But yeah, powerful way of organizing things. I think we should use them a bit more often. Okay, and I mentioned this a little bit earlier too, seeing exception blocks as transaction boundaries. Okay, that's a rather powerful thing for us to think about also. And the thing is, I talked about that worlds thing that they're putting into this research dialect of JavaScript. But really, I think this is really more of a practice thing than anything else. It's kind of like for us, going and looking at things and saying, it's like, what do I really know about the state of the world, when I get out of this try-catch block? Can I possibly put things in an inconsistent state after doing this? And if you can, then you're in trouble. The thing which is kind of important with this also is kind of like the thing about designing away preconditions. It's like, the bigger your preconditions are, the more a chance you have things wrong. In much the same way, if you have a try-catch block that goes and extends over a vastly large computation, right? And you can't really tell yourself that, wow, the state of the world is going to be the same after I do this, regardless of whether it's, if it fails. If you can't tell yourself that, that probably means that you're using exceptions at a higher level than you probably should. And it would be nicer to move back towards that thing I was talking about a bit earlier, where you say, okay, look, it's like I should be validating all my input and then performing all my computation doesn't have to worry about errors, and then going ahead and perhaps validating output. And have to not really worry in the very center about bad things happening. So you all know who Ron Jeffries is, right? Okay, first coach on the C3 team for XP. It was funny to talk to him one day and realize that he felt the same way about exceptions that I do. He just doesn't like them all that much. And in fact, he was rather derogatory. He basically used to call the construct hurl, which is, I guess, like 80s slang for vomiting. Right? So you don't know what to do, so you hurl. You just kind of get out of things. But it is an interesting kata to do. It is an interesting thing to try to do when you're working in a system, to go and ask yourself, gee, except for the exceptions that are being thrown by APIs that I'm using that I didn't define, is it possible for me to design my system without exceptions? And if you can do that, it's kind of powerful because it sort of forces you to deal with particular things, and it can help you reorganize your code in ways which might be a bit different, but you might be able to learn from it as well. So it's a decent thing to go and try out. Okay. Another thing to mention too is this thing of knowing your profile. Okay. Was the thing I was talking about in the very beginning. Is your system technically attentive? Are there people who are going to be able to be there to fix problems when they occur? How critical is continuous operation? All these things factor into how you actually go ahead and put error handling and into your application. And we do tend to think of these things as being afterthoughts, but really, being aware of this profile during the process of when designing your system, during the process of going and settling the initial things. Many of these things, given the language constructs we have today, end up becoming pervasive code-based things, where it's kind of like you make a decision to do something like this. It's kind of like, well, you know, if you're doing one type of system, you really want to use exception for this particular way. If you're doing another type of system, you really want to go and use that thing like an error handler that you pass around. And that affects things at a rather deep level all the way across your code base. It affects whether you use null objects or not, things along those lines. So really being able to answer this question for yourself as you're first designing a system is a great thing because it gives you that kind of context in which you can basically use, context in which you need to go and decide about how you're going to go and deal with error handling and going through the things. Another thing to point out with this too, there's a great book that's going to be coming out pretty soon called Growing Object-Oriented Software Guided by Tests by Steve Friedman and Nat Price. How many people know who Steve Friedman is? Okay, a bunch of people. Nat Price, another great guy. These guys live in London. And actually, Steve Friedman, the main thing he's really known for is that he did the first paper with a co-writer back in like 2000 or so that first described what mock objects were. And mock objects were something that they basically came up with at Connextra, this company in London. And they basically came up with the idea of putting an assertion inside this object and basically passing it to some object you want to go and test. And they wrote it up. And of course, since then, we've had many different frameworks that do mock objects and things along these lines. The thing that's kind of fascinating to me about this, though, is that they have arrived in London at a slightly different style of doing TDD than most of us do in North America. And I think it's just really a historical thing in a sense. It's kind of like, it's kind of like playing a game of Chinese whispers or something like that. In the early days of TDD, you had Kent Beck and Ron Jeffries going in. This is another thing which is kind of funny. I saw in the J programming language a construct which I thought was really, really kind of cool. So I coded it up in C#. And it was an operator in J called adverbs. And does anyone here read C# at all? Yeah, cool. I mean, it's just like Java, but with uppercase. That's it. And they did that, so we could tell the difference. But this little class here, okay, we have a static thing called call. What you do with a call is you basically go and pass two functions to it, okay, two lambdas. You pass an attempt function and a recovery function. Okay? And so this is kind of neat because it's always it kind of gives you this thing where you can say, look, I want to go ahead and do something here. I think you can see this from where you all are. Adverse.call get line, and then we're basically saying, we have this lambda here, we'll basically say that we're passing a function that goes and accepts an argument and just goes and returns back an empty string. So what this call is doing right here is saying, look, we're going to go and call get line. And if get line fails for any reason whatsoever, we're just going to return back an empty string. So it's kind of like a way of doing that normalization business where you say, look, I'm going and I'm doing my computation, and it's kind of like something bad could happen, but if something bad happens, I don't really care right now because I'll just get back an empty string, and my program knows how to deal with empty strings. And the empty string is just like a valid case that means you just don't have anything, and it runs all through the system, nobody cares about it. So it's kind of like a null object scheme in a sense. But the thing that's kind of neat about this, though, is I think that there's a cool thing that if we did this sort of thing more often, we basically going to start to have a more disciplined approach towards how we detect errors and constrain them. And the reason why is because when you're doing this, you're forced to create two different functions that you can pass in. The thing you want to detect and the thing you recover with. And that's just like try-catch in a way, right? Except this is like a functional try-catch. This is one which is forced to return back to you a single value. How many times have you seen try-catches do things more than that? Right? I mean, you can do all sorts of crazy, crazy stuff in a try-catch, right? Because you have available to you all the state that's within that same method and the state that's available within the same class and that other stuff too. So a construct like this is kind of neat because it sort of says, look, being really structured about the way we go and organize errors or error detection, and we just want to go ahead and say, look, we're going to do this sort of thing. And you can actually go ahead and chain these things. You can chain calls and say, look, I'm going to do this and this and this and this and this. At any point, if anything goes wrong, just the null value or the null object value gets propagated back. Okay? You can also create a version of this which is just void functions. And it's almost like the chain responsibility pattern in a way, where you say, look, I've got all these calls, and it's like I'm just lining them all up, and I'm saying, look, I just want to keep on doing things until I'm not able to do anything anymore. If I can't do anything anymore, then I just stop and then blow my computation. So there are many things like this which people end up trying to do with control flow constructs. And often it ends up being kind of crazy in a sense. But with some of these things as primitives in a way, we can actually go ahead and do, handle errors and have different types of control flow in a rather decent way. So one last thing to talk about in this context too. I was talking earlier about this thing of going and converting things into good values when we receive invalid input. A thing which is almost like kind of outside the scope of this, because this is really more about code and stuff like that, is really how we handle input at all within an application. And I think we've made great strides over the past, I don't know how many years now, 10 years or something like that, and having people kind of recognize that you can organize user interfaces in a way where it's impossible to produce bad input. Okay? I mean, classic example of this is kind of like you can give people a text field to go and enter stuff, or you give them a set of radio buttons, right? And click one of three options. That's way better than going and giving them an open text field where they can just put anything they want to in it. And it's like, when they have a set of constrained choices, they're able to go ahead and basically give you something and you always know it's valid. And it takes a little bit of finessing sometimes to go and basically organize user interfaces in that way. But it's worthwhile. Okay? Fewer possibilities of errors in the system, fewer things to validate, things along those lines, and you can go ahead and end up having, I guess, better and safer code. So I'm ending a little bit early. This is really all I have on this, and it's just basically a set of things I've been thinking about with this sort of thing. I'm kind of hoping to write up more of this stuff because I think it's something which is kind of, we haven't thought about enough in the industry. And I'd love to go and get y'all's comments and anything else you think is really cool that kind of belongs with this. So, any thoughts at all? Yeah.
I think I saw a paper in, 2003 UXLA on failure oblivious computing as a special case of acceptability computing, whereby the notion is very much in the case of your embedded systems example of how do you keep going, and they went back and did that to a whole bunch of the Linux stack in particular, as well as user-based applications, and said, what's the if you corrupt or if you have bad data, is that worse from a systems engineering perspective, or continuing with the failure intact?
Yeah.
I thought that was a really interesting chain of thought.
Yeah, I have to look into that. It's a funny thing. There are systems that definitely are like that, and I'm assuming that what they're getting at with that is just how do you make that choice, right? Which is the proper way to go with the system.
Because aborting it often leads to security problems.
Okay. Yeah, no, thanks. Look at that. Yes.
I have a thought.
Sure. Yeah.
I've seen some misimplementations of the null object pattern in which the programmer decided to create an object of the same type, but it had null state. It had all the same behavior, but it was an invalid state. And that propagated through the system with a bunch of validity checks to see whether this was a real object or not. So that's, when I saw that pattern again, I'm a little traumatized by that.
Maybe I'll repeat that because just to make sure everybody heard that. Yeah. She was saying that she saw basically bad examples of use of the null object pattern where basically what happened is people code them in such a way that they kind of had some invalid state and stuff, and ended up producing lots of checks elsewhere in the system.
So instead of extending and making another subclass called, for example, null employee,
yeah,
it would be an employee with a null ID or an empty string for a name.
Yeah.
So that.
Okay, yeah, that is bad. But it's funny that null object because when people talk about it, they rarely think about the case where it's like, an empty string can be a null object, right, or an empty list. Yeah. So it is like the same concept can be applied in many different ways. And as an implementation choice, you can choose to go in subclass and create one.
Yeah.
Or you can choose to go and basically take an existing object and kind of mock it up in such a way. The key thing with null object more than anything else is basically determining whether the null object you create is going to be able to play well in the rest of your system. And if it's not going to be able to play well, and people are going to have to go and do things like checks later on in your system, then what you've done is you've established another one of those private languages I was talking about, where it's kind of like we encode information over here, and we have to decode it over there.
Yeah.
And that's just, it's a bad case. But I think what it comes down to for that is really just sort of knowing, will we have to go and actually ever know that it really is a null object? When Martin Fowler wrote up the null object pattern, or a null object write-up in the refactoring book, he talked about moving towards it and having like an is null check on it, which is cool, but I think from a pure point of view, you'd love to not have that in a new system that you're writing, just so that people don't care. But were you going to say some more?
So that's the thing. It's important to really think about the implementation of the null object. And
Yeah.
then the other example that you gave about error fainting, with that specific example, if there was a field called column index,
Yeah.
and outdent was called one too many times, then you would, if you were normalizing,
Yeah.
you would end up with an invalid state. And I've seen bugs created as a result of normalization on behaviors
Yeah.
if the object is stateful.
Yeah, I think so. Yeah, I see
So
what
the
you're saying.
column
there.
index of the number of,
Right.
if that's a property that's used elsewhere in the code,
Right.
you want to be able to rely on that property
Yeah.
just for that specific example.
Yeah. No, that's fair. Yeah, and it's funny. I don't like doing that, but I just offer it because it's something which is useful sometimes.
Yeah.
But it is a bit of a deceptive thing because you're looking at the API and you're thinking, well, I kind of understand what's going on here, but then it's like it's just trying to be far more liberal with input than it should be necessarily. There's something else that this comes back to. Have you ever heard of like Pastrol's law at all, or something like that? This is something that was Pastrol's law. I think I'm right about this. I could be wrong. Maybe someone else can tell me. But in Unix, when the early days of Unix, when people were going to establishing like pipes and filters and all this other stuff, they said, okay, a great thing to do is to be really liberal with your inputs, but really constrained with your outputs. And then that basically goes and makes the system pieces very adaptable when you're chaining things together. You can say, look, I can kind of accept, a little bit more of this, a little bit more of that, and be just a little bit more forgiving. But I'm always going to give you dead center. It's going to have this particular spec thing I'm going to produce for you. And that tends to be rather an interesting approach to systems design, to go and organize that sort of thing. And I think error find is kind of like that in a sense, but at the lower level API thing. But yeah, I agree, it can be confusing. So it has to be used, with
It's a tool in the toolbox.
There you go. So, yeah.
You were mentioning that there's two kinds of ways to handle attended and unattended errors. One is you fail fast, and the other one you soldier on. There's sort of a third problem we run into when we're in an embedded system.
Yeah.
You're not allowed to fail on user input because user input actually could be like a router, and anything that comes in should not crash your system, no matter what it is.
Yeah.
But on the other hand, we can't give bad results. Okay? The results have got to be something that is understandable, and the problems we have is related mostly to customer report errors or system tests that don't understand if it's the stimulus or the device under test, or if it's our software they're trying to think. So the
Yeah.
embedded system, how do we know who's at fault, right?
Because you're doing the work of normalizing,
Yes,
you're trying
we can't fail on whatever comes in, but on the
Yeah.
other hand, our data has to be good. Because
Yeah.
we have a lot of times a problem trying to have it so we can prove that it's not our embedded system, it's actually these
It sounds to me like a case for some kind of logging or notification where basically what you do is record the fact you are doing that work, and then maybe you're able to go and check afterwards and say, it's like, okay, well, it's like, yeah, you're getting this particular thing, but it's like we know that essentially we had to do this work to go normalize things. I don't know if that applies in your case or not.
Yeah, there's some places where we can do that, but
Yeah.
we've run into problems for once in a while in the past where we don't expect some kind of data and it'll start causing things further down the system that are really hard to trace.
Yeah, or, yeah, no, I think it's.
So I think there's like sort of a third class between
Yeah.
attended and unattended. There's a hybrid thing in the embedded system.
Yeah, because I know that's not a perfect classification, but thanks for that. I'll try to incorporate that. Yeah.
One of the things that I've seen quite a bit of is really anemic exceptions, and they just, in Java particularly, there's an extend exception, and then they throw them.
Yeah.
And I think with this, it forces you to think through a bit more because you've separated your logging out into your separate bit. You've got to put the state in the exception that caused it.
Yeah.
So, and you don't, because it's not available in the method that you're in. You've separated it out, and that may force you to think about the design of your exceptions more.
I agree. I think that's one thing I really think is an underappreciated thing about programming in a sense. I think that there's this cool thing where basically the constructs that we design have, Kevin Henley calls this like affordances. It's kind of like there's what's that guy, the design for everyday things, Norman? Donald Norman, okay? And he uses this term affordance also. It's kind of like when you have a particular programming construct or your code's organized in a particular way, people are going to come in there and make changes, and it's like essentially the way that they do these things is going to be affected by what's there already. And so in much the same way, if you basically give people an abstraction like this and say, hey, this is the way we handle things, then they will quite possibly end up with something which is better and doesn't really have those issues. Of course, you could also have other bad side effects because it's just you're dealing now with a new state of possibilities, a new state space of possibilities. But, yeah, I agree. Yeah.
So similar to the adverse class, you mentioned Uncle Bob's stack janitor or C++ or C#. It's a class that implements a software transaction.
Yeah. What's it called again?
Stack janitor.
Okay.
And you just keep adding operations. You call an operation and you provide the undo for it. And you can execute a sequence of them, and if you don't call commit before the destructor happens, i.e. through an exception, then it undoes everything in reverse order of what happened.
Yeah. That's cool. And it's funny because a lot of these things are things you look at them, it's like we can mimic them with objects, we can create them with objects, but some of them, when you get down to it, they really are control constructs in a way. It's like just for chain computations and stuff along those lines. I think it's kind of cool in a sense because with functional programming, which I've been getting into quite a bit more recently, you don't really have common state across things, so instead you have to go in kind of chain computations. So a lot of these things which end up being more control flowish are kind of, you end up going and making these things yourself, and it's kind of neat to see. So. Yes, any other questions or comments at all?
Please. Just for the gentleman that was stack generator, in C++, in C# is the destructor guaranteed to be called?
So in C# you put it in a using construct and you put it in a using construct. Yeah. You just make it disposable in C#.
Okay, well, thank you guys very much.